So, myself, Gangadhar, I'm an assistant professor in Deemed University. So, today we are going to discuss a sorting algorithm called merge sort. So, before getting into details, let us see a definition about what is merge sort. So, merge sort is a divide and conquer sorting algorithm. So, what it is going to do? It is going to divide the array into two halves and then recursively sort both the halves, and finally it is going to merge both the halves into a single array. So there are three key steps in a merge sort. First is divide. It is going to divide the array into two equal halves. Based by finding the middle element, it is going to divide the array into two equal halves. Second step would be conquer. It is going to recursively sort both the halves. Once we have both the halves sorted, then the third step will be combine. Using a merge procedure, we are going to whatever the recursively sorted arrays we have, we are going to merge it into a single sorted array. Now let us see with an example how the merge sort is going to work. Now we have an array that consisting of 8 elements. So as I told you, the first step of the merge sort would be recursively divide the array into two halves based upon the middle value. So what is the middle value here? Since there are 8 elements, so exactly it will be divided into two halves here. First half will have 85, 24, 63 and 45 in the left half, and 17, 31, 96 and 50 in the right half. Now the recursive division continued to happen until we have one element left in the array. Now we have 85, 24 in the left half, and in the right half we are going to have 63 and 45. So similarly this will be divided into 85 and 24. Now if you see here in this array we have only one element left. This is where the recursive division is going to stop. Now what will happen after this? Now after this, as the array consisting of only single element and the single element itself is sorted, now this is going to return 85. So similarly, this is going to return 24. Now here we have a sorted half and we have a sorted half. Now merge procedure is going to happen. A merge procedure is going to compare these two elements, and this is going to replace in a sorting way. 24 will come here and 85 will come here. So similarly, here also this is going to return 63, this is going to return 45 because single element itself is sorted. Now this will be replaced as 45 and 63. Now let us see how the merge procedure is going to work at this point of step. Now we have two sorted halves, right? One have 24 and 85, and another we have 45 and 63. Now how the merge procedure is going to work? We have low here and we have high here. We will see what is low and what is high when we get into the code. Now I am going to assign I to this array, and I am going to assign a j pointer to this array. So how the merge is going to perform? We are going to have a temporary array that is going to consisting of 4 elements. Now here 24 is compared with 45. So 24 is less than 45. So 24 will be placed here. Now after that I will be incremented here. Now again 85 is compared with 45, but it is greater. So which element I have to place in my temporary array? 45 means this one. So I am going to place 45 here. Now I am going to increment my j pointer. Now again same, 85 is compared with 63. Since it is greater, which element I have to place first? 63. Then 85. So this is how the merge is going procedure is performed. So similarly, here what will happen? What is the resultant array after performing the merge operation? This array will be rearranged as 24, 45, 63 and 85. So similarly, this will be rearranged as 70, 31, 50 and 96. So now finally let us see how the merge operation is performed on at this point of step. 24, 45, 63, 85 is my left half. The right half is 17, 31, 50 and 96. Now same, I'm going to assign I pointer here and I'm going to assign J pointer here. Now we are going to see one more time how the merge operation is going to perform. Now 24 is compared with the 17. Which one is smaller? This one is smaller. So in the resultant array, which one will be, we have to place 17, we have to place, and we have to increment J pointer. Now again 24 is compared with 31, so 24 will come here and I am going to increment my I pointer here. Now after that my I pointer will be here. Now again 45 is compared with 31, which one is smaller? 31 is smaller, I am going to place it and I am going to increment my J pointer. Now again 45 is compared with 50, which one is smaller? 45, so I am going to increment my I pointer. Now again 63, 50, which one is smaller? 50 is smaller, so I'm going to place it here. I'm going to increment J pointer. Among 96 and 63, which one is smaller? 63 is smaller, so I'm going to increment my I pointer. Among 85 and 96, 85 is smaller, so I'm going to increment my I pointer. Since one of the pointers become out of bounds, now whatever the left out elements, just copy those elements as it is. Now this is the sorted array. Now let us see the pseudocode of the merge sort. How does the merge sort pseudocode looks like? This is the logic of the merge sort pseudocode. What are the parameters? We are going to have three parameters. One is the array, another is a low pointer, another is a high pointer. Now we are going to run merge sort until low is less than high. So initially the first step would be calculate the middle value. So based on the middle value, I am going to call the merge sort from low to mid and mid plus 1 to high. And finally, the last step would be the merge procedure, that is going to merge from low to mid and mid to high. Now let us see this example. This is the example I just now discussed. Now this is in terms of, so let us see. Initially, this is the thing, and 85, 24, 63, 45 will come here, 17, 31, 96 and 50 is going to come here. So similarly, this will be divided into again two halves, 85, 24, 63, 45, and then 85 will come here, 24 will come here, and so on. Now, after that, let us see the merge function pseudocode. As I told you, merge is going to divide the array into two halves. So, we are going to have two temporary arrays, L and R. We're going to copy the left half elements into array L and right half elements into array R. So initially I'm going to initialize I equals to 0, that will point to the left half, and j equals to 0, that will point to the right half, and k equals to low. Now how until I less than size of the left array and j is less than the size of the right array, I am going to perform a merge procedure. If my left element which is present in the left half is less than or equals to the element which is present in the right half, then I am going to place the left half element into the my original array or a temporary array A, and I am going to increment my I pointer. Similarly, if this is not the case, I am going to place my right half element into the array, and I am going to increment my j plus plus, my j pointer, and finally After we come out of the while loop, we are going to copy the remaining elements of L and R if any remaining left out elements are there. Now let us see the performance analysis. What is the time and space complexity of merge sort? Have you, if you observe here, merge sort is a recursive function. In general, we are going to calculate the time complexity of a merge sort by, or in any recursive algorithms, by recurrence relation, right? So this is the recurrence relation of merge sort. T of n is the number of elements, and T of n is the time taken to execute the n elements, is equivalent to 2 into T of n by 2 plus n. What is this 2 into T of n by 2 plus n? Let us see. We know that we have the merge sort is going to recursively divide the array into two hops, right? So if you see there are n elements, there will be n by 2 elements will be here, n by 2 elements will be here. So always, if there are n elements at each level, half of the elements will be in the left part and half of the elements in the right part. So it will be like T of n equals to T of n by 2 plus T of n by 2. What is this plus n here? This is the time taken for the merge procedure. So T of n equals to 2 into T of n by 2 plus n if n value is greater than 1. If n value equals to 1, then time taken to execute that one element will be 1. Now whenever we have a recurrence relation, how to calculate the time complexity? By using two methods. One is the old method, which is batch substitution method, and another one is using master's theorem. So since if I'm not using master's theorem here, because I have to again explain the basics of Master's theorem formulas and all. So let's go with the old method, which is batch substitution method. So T of n equals to 2 into T of n by 2 plus n. So this is the equation 1. So now I don't know the value of T of n by 2 here. So I'm going to simply substitute in place of n by 2. Now what will happen? 2 into T of n by 2 plus n by 2. What will happen? 2 into T of n by 4 plus n by 2. So this is equation 2. So now I don't know what is the value of T of n by 4. So I am going to substitute T of n by 4 in equation 1, not in the equation 2. So what will happen? 2 into T of n by 4 by 2 plus n by 4. And what will happen? 2 into T of n by 8 plus n by 4. This is equation 3. So let's substitute equation 3 and equation 2 in equation 1. Now what is equation 1? T of n equals to 2 into T of n by 2 plus n. Now let us substitute. What is T of n by 2 here? 2 into, what is T of n by 2? This value, right? So 2 into T of n by 4 plus n by, so remaining n, and I am going to place it here. And what will happen? This will be equivalent to 2 square T of n by 2 square plus n plus n, it will be 2 into n. Now similarly, and I'm going to substitute this 2 square T of n by 4 plus 2n. Now I have T of n by 4 value. So similarly, I'm going to substitute again. 2 square of, what is T of n by 4? Here, this one. 2 into T of n by 8 plus n by 4 plus whatever the left out element, which is 2n. Now what will happen? Let us see. Let us observe a pattern here. Now it will be 2 cube T of n by 2 cube plus 3n. If I substitute and so on, what will happen? This will be 2 power k T of n by 2 to the power of k plus k into n. Now we have to replace these k values in terms of n values. And now what is this one? What is T of n by 2 to the power of n by 2 to the power of k means, what is t of n by 2 to the power of k? N by 2 to the power of k number of elements are present. And when the merge sort is going to stop? When we have one element. So I'm going to equate n by 2 to the power of k to 1. Now what will happen? N equals to 2 power k. Take log on both sides. It will be k equals to log n base 2. Now substitute the k value in the, replace this k value here. What will happen? 2 to the power of log n base 2 t of 1 plus log n base 2 into n. Now 2 to the power of log n base 2, the base and this one is base is matching, so it will be, what is the value? N into t of 1 plus n log n base 2. We know that in the recurrence relation t of n will be 1. So n plus n log n base 2. How we are going to express the time complexity in terms of big O? So among n and n log n, which is the most dominating term? N log n. The big time complexity is the big O of n log n base 2. So this is the time complexity of merge. Now, whatever I have discussed here, that is present in the slides. At each level, array is divided into two halves. Merging takes big O of n time, and this is the recurrence relation. Now this is the back substitution method I just solved now. Just have a look. Final time complexity would be big O of n log n. Now let us see the space complexity. How we are going to find out the space complexity. Whenever the program is a recursive program, it's always best to draw a recursive tree. If you draw a recursive tree, finding the space complexity will become much easier. If you see there are n elements, what is the merge sort is doing every time? It is going to divide into n by 2, n by 2. And each level it is again going to divide into n by 2, n by 2, and so on. If you calculate the cost at each level, what will happen? At level 0, the cost is n. At level 1, the cost is again n. And at level 2, the cost is again n. So the cost at each level is n. And if you see, this is a fully complete binary tree. And the depth of this fully complete binary tree or height would be big O of log n base 2. So this log n base 2 is a recursive or stack space. Now we know that in space complexity, there will be auxiliary space plus the recursive space. Now we have seen the recursive space is log n base 2. Are we using any auxiliary space here? Yes. In merge sort, the auxiliary space we are using is for temporary arrays. If you remember, every time after recursively sorting both the halves, we are going to take a temporary array of size of the left half plus size of the right half. Those are the temporary arrays, and in the worst case n elements will be stored here. So temporary halves, extra space will be big O of n. The recursive stack is going to take n log n, and the entire total time complexity will be big O of n, because big O of n is the most dominating term. So this is all about the merge sort. Now let us see the complexity analysis. In general, if you talk about any sorting algorithm, we discuss about the worst case, and the average case. But in merge sort, there is an interesting case. In all the cases, the merge sort behaves the same. The best case is n log n, the average case is n log n, and the worst case is also n log n. Why? The reason is, here the merge sort divides the array into two halves irrespective of the element order. Even if we give the merge sort a sorted array, it's still going to take big O of n log n. So that is the best case is going to take big O of n log n. The space complexity is big O of n. Now let us see some important points about the merge sort, apart from how it works, what is the time and space complexity. Now merge sort is a stable sort. What do you mean by stable? Stability means equal elements maintain their original relative order. For example, if you have an array that consisting of duplicate elements, even after the sorting, the relative order should be preserved. Let us take this example: 5a, 3, 5b, and 2. After sorting, what will happen? 2, 3 will come first. Among 5A and 5B, which one has to come? Why I have taken A and B? To just to differentiate which 5 is different from which 5. So 5A and 5B here. According to which one in the input, this is the one that is coming first, right? So in the output also it has to come first. So this stability will be preserved by the merge sort. So that is why merge sort is a stable sort algorithm. Now, merge sort is an out of place algorithm. What is this out of place means? You heard about in place sorting algorithm. Means given an array, we have to make the changes in the in place inside the array itself without taking extra memory. But here in merge sort, we are actually requires an additional memory for merging, which we have taken temporary arrays. So that is why it is an out of place algorithm, not an in place algorithm. The third one is merge sort is used as an external sorting algorithm. So merge sort is suitable for sorting large data sets that do not fit into the RAM. It divides the data into smaller chunks, sorts them separately, and merges them efficiently. So this is external sorting thing is generally used in databases, data warehouses, and big data applications. Now, one more important point: merge sort is preferred for linked lists. Merge sort is not preferred for arrays. In general, quick sort is preferred for arrays. Why? Merging can be done. If you see, the merging can be done using the pointers instead of moving the data, right? If you see the merge procedure, we are compared and just we have replaced the smallest element into the temporary array. So here merging can be done by changing the pointers instead of moving the data. And here there is no random access is not required. But if you are dealing with arrays, random access will be there. So if you see linked list, there is no random access. That is one of the reason. Random access is one of the most important reason why merge sort is preferred for linked list. And here splitting the list is easy using the slow and fast pointer technique. So that is all about the merge sort. So that's all. Thank you.